Okay, so welcome to the series of online interactive lectures which have been organized in this by the INO project. And today we are in the 15th week of these lectures, and today's talk is going to be delivered by Professor James Libby, that is, from IIT Madras, and he's going to talk on the Belle II, flavour physics, and more at the intensity frontier. Just a couple of minutes on today's speaker. He's an experimental particle physicist working at IIT Madras, as I said, since 2009. Professor Libby received his undergraduate and postgraduate degrees from the University of Oxford. His PhD work was largely based on the European Centre for Particle Physics, that is at CERN, Geneva, for working on electroweak measurements at lepton. Since completing his PhD in 1999, he has worked principally on flavour physics with accelerator experiments at CERN, Stanford, Cornell, Decays, that is Japan, and also higher in China. So that is his vast experience in flavour physics, and today we can look forward to a very exciting lecture from him on this topic pertaining to Belle II. Yeah, so Jim, over to you.
Okay, so thank you, Satya, for both the introduction and also the invitation to give this talk. So I will be discussing the Belle II project and flavour physics, and I should be clear from the beginning here, I'm talking quark flavour, not lepton flavour. So that means I'm going to do some sort of pedagogical introduction as well about why the quark sector is an interesting place in terms of particle physics, and that's where the intensity frontier comes in. So for the overview of this talk, I will just introduce this idea of the intensity frontier first and what we're trying to address by such experiments as Belle II that operate at the intensity frontier. And then I'll describe some history, which is quite appropriate for what we're trying to do. So give some examples, actually textbook examples of things that we've learned from flavour measurements in the past, and hence why we think this isn't a suitable place to look for new physics today. So essentially it is flavour as a predictor of higher mass scales than that of the beauty and charm quarks that we're looking at. So that naturally then leads me to the precursor to Belle II. So to understand Belle II, you must understand Belle initially and its legacy. And also many of you will be aware that there is another flavour experiment, which is rather different in its strategy, that operates in proton-proton collisions at the LHC. And I'll try and describe to you in a single slide why two different experiments are a very good idea for flavour physics in different environments. And I'll talk in more detail about Belle II. I'll discuss some highlights of the instrumentation, particularly actually I should say SuperKeck B, the accelerator here as well, and show some recent results, actually so recent that they're taken from the ICHEP talks that are going on today. And then I'll give just one physics prospect to give you an idea of what might be achieved in the next few years before I conclude. So Belle II is a running experiment, and this is what our events look like. This is an E plus E minus collision producing an upsilon 4s event. So there are a couple of things which I'll come back to in the talk, is that it's not like the event pictures that you see at the LHC. There are relatively few tracks involved, and many of them are low momentum, hence they're curling around. But it's very much an active experiment now. This is probably the first B event that we saw back in 2018. And also we're at a stage where we want to exploit. And for those of you who are interested in the physics that I talk about, the best place to look is this rather intimidating document that we published last year, but was put on the archive in 2018, which is a physics book which describes the whole physics program. And there's no way I can do justice to everything because there's so much else going on. And I'll come back to this at the end. So this is just some places where you might want to look beyond this talk. So the standard model, you should know this picture well, whereby we have our classification of particles into those of matter, the quarks and leptons, and then the force carriers, as well as the Higgs boson. And this picture has been tremendously successful since it was first put forward. And it's quite hard to actually understand how successful this has been. It's really confronted pretty much every single experimental challenge that's been put up to it. And as a result, as it was built up, it's been highly rewarded in terms of Nobel Prizes. Much when I give this talk to non-particle physics people, this is somewhat frustrating to them. So just to quickly go through how successful this has been, there have been Nobel Prizes, first starting with Gell-Mann for understanding quarks, and then Ting and Richter won for discovery of the charm quark. Then the overall standard model structure, Weinberg, Glasgow, and Salam, was given the Nobel Prize. This was followed by CP violation in strange quarks for Cronin and Fitch. Then Rubia, Demir won for the W and Z boson discovery. Then Steinberger et al. For the muon neutrino, showing there is more than one type of neutrino. Then the discovery of partons with Taylor, Friedman, and Kendall at SLAC. Then Reines for discovery of the electron neutrino. Then Martin Pearl the same year for discovery of the third generation, the tau lepton. Then 't Hooft and Feldman for showing that a locally gauge invariant quantum field theory, relativistic field theory, is renormalizable and hence is a suitable way to describe the interactions. Then you have Gross et al. For the understanding the strong interaction. Kobayashi and Maskawa, who you'll hear more about later, for predicting a third generation to describe CP violation. Then Nambu in the same year for spontaneous symmetry breaking, and then finally Higgs and Englert. So this is, I think, 14 Nobel Prizes for this one model of particle physics. But we know it's wrong. There are many problems with this, some of which are empirical. Most noticeably is that neutrinos are massive, which I'm not going to talk about in to this audience, but that also is the only thing of particle physics that's beyond the standard model that's won the Nobel Prize. Dark matter, we don't understand whether it has a particle nature and what is that particle. Dark energy, I don't think we know it's there or appears to be there from cosmological observation, but is there some link to particle physics? We certainly live in a matter rather than an antimatter universe. How did that arise? That's not explained by the standard model, and of course gravity is missing. Then there are aesthetic issues with the standard model as well. Why 3 generations? A priori, that's not required, and why not 4? Why not 5? Why only 3? Why this structure? And also, why so many parameters are required to describe this? So I've excluded neutrinos. I've said neutrinos are massless within the standard model. I've taken the masses to be beyond that with 18 parameters. And then also why they have a distinct hierarchy, again, something I'll come back to. And of course, there's fine-tuning problems, the hierarchy problem, the 18 decimal places by which you need to know these parameters. And overall, you would like to unify all of these into one single theory, including gravity. So we approach this in 3 different ways in particle physics experiments. These are the so-called frontiers. One has the energy, the cosmic, and the intensity frontier. And this pretty much makes up all of experimental particle physics. So for the intensity frontier, that's the LHC. This is a plot from Atlas showing the limits that they set on beyond the standard model supersymmetric extensions from their various measurements. So this is trying to produce massive new particles at the TeV scale directly and then observe their decays inside the general purpose detectors. So this is one route to discovering new physics. Then you may well have seen plots like this. This is not quite up to date. This is from the PDG, where you're looking at the detection of a WIMP-like candidate for dark matter, a weakly interacting massive particle, where you have these very sophisticated experiments, often working in cryogenic environments, trying to detect the small amounts of energy deposited when dark matter scatters off a nucleus. And these limits are pushing down now to very low cross sections, and to what might be the limit when you actually start having background coming from neutrinos in these experiments. So I apologize, you're going to hear a cat occasionally in the background. I can't do anything about that at the moment. So, and she will choose the most inopportune times to start shouting. So that's the cosmic frontier, but what we're interested in this talk is the intensity frontier. So from neutrino physics, if you take an intense beam here generated by J-Park and fired towards the Super Kamiokande detector, you have the T2K experiment, and they measure the number of protons on target that they have as their sort of measure of the number of neutrinos they produce. And you see this is just a program of trying to get as many events as possible to measure parameters precisely. And that's exactly what we're going to be doing in the Belle II experiment as well. We're going to work at this so-called intensity frontier, which is all about getting as many events as possible and doing precision measurements and searching for very, very rare decays. So that's oriented ourselves as to where the intensity frontier fits in terms of Belle II. And Belle II in principle can tackle virtually all of these problems. So the flavor puzzle in terms of why we have 3 generations in the hierarchy is very much at the forefront of that. But we're also indirectly sensitive to many other things as well. And whatever standard model, beyond the standard model physics there is, should affect some of the measurements that we have. And if we don't see anything, these null tests that we have will also suggest that the mass scale of any new physics is extremely high. So those in reds are things I think Belle II can in some way address. So flavor physics now, the history of this. So as I alluded to with my slide on the standard model, in the early 50s and 60s, there were many, many particles and not much sense could be made of them. Some were considered strange because of the way that they decayed. But Gell-Mann and Zweig put order upon this by suggesting the quark model. And by understanding that these particles that have been observed have been made up of these 3 quarks, you could very much explain the lowest lying nonets of mesons and the octet and decuplet of baryons, as well as some other particles that were observed. So with these kind of discoveries, you can actually study these particles more and more. And an example of a rare decay, very much in the flavor sector, is where you have this rare decay of a long-lived neutral kaon going to two muons. So this is less helicity suppressed than the electron version of the decay. And so how this proceeds in the standard model was that you would have this second order weak diagram where you have this box where you have the flavor transitions of the quarks mediated by the W on one side to annihilate your neutral kaon. And then on the right-hand side, the final state, you'd have leptons linked together by the Ws. And this could be written down and thought about in terms of second order weak interactions. But the problem was that this decay was not seen at all. So how this was resolved was by these 3 gentlemen, Glashow, Iliopius, and Maiani, so-called GIM mechanism, suggested that a way to get around this was to have a 4th quark. So at this time, there's no experimental evidence for this 4th quark, but they suggested this to fix a problem in terms of a flavor observable. And here, once you introduce the charm quark, you get a second diagram, where instead of the virtual U quark being exchanged between the strange and the anti-down quark, you have a virtual charm quark. And once you add in the various Cabibbo factors to this, you see that there's a sign difference between these two different decay diagrams, two amplitudes. So once you sum those coherently and square them, up to effects related to the difference in the up and the charm quark masses, these two diagrams cancel each other out, giving you a rate approximately equal to 0, hence explaining the rate of suppression of this decay. But because the up and the charm quark are not quite degenerate in mass, the decay does actually happen, and at a rate which you can then postulate what the mass of the charm quark was, which people did. But this is an example of a virtual process. You're not directly observing this charm quark, which has roughly 3 times the mass of the kaon, by looking at this process, which is actually at a lower mass scale. And that's the whole idea behind making precision measurements in the flavour sector. So another example, quickly, is that when B mixing was observed, I'll talk more about B mixing shortly, this was seen by having 2 Bs decaying, where they both decayed to the same charge of lepton, suggesting the B mesons had, one B meson at least had oscillated. And the rate at which one saw, so yeah, I've drawn the diagrams. It's very similar to the kaon diagram, but now with quarks on either side, and again you have this box. But in the box, because you have beauty in the top quark, there's a strong coupling between these two, so it's dominated by the top quark. So the rate at which this happened told you that the top quark was very, very heavy compared, say, with the scale of the B meson, and much beyond the scale at which people were trying to observe it, even though UA1 had optimistically claimed its discovery at the SPS back in 1984, but the mass was far too light for this to possibly have been discovered there, and you had to wait till the Tevatron before it was seen directly at 175 GeV. So these are examples of where flavour measurements have been able to predict physics at higher mass scales. So to understand a lot of what we do in terms of the measurements at Belle and Belle II, we have to look at the CKM matrix. So I've already mentioned the Cabibbo couplings in the first 2 generations of quarks. And this came about by this 2-dimensional, 2x2 mixing matrix between the flavour states and the weak states. So the states that couple to the W's, the weak states, are admixtures of the down and the strange quark. And to preserve unitarity, you have this kind of rotation matrix. Now, Kobayashi and Muskawa, who I've mentioned, they made the bold prediction before even actually the charm quark had been observed, that to have CP violation, as seen in neutral kaon decay, you needed a 3rd generation of quarks. And they had this 3x3 matrix, which is just the extension of the Cabibbo model for quark mixing. And why they said you needed 3 generations was because to describe this 3x3 unitary matrix, as well as using the ability to take phases that are unobservable into the quark fields, 5 of those, you can show that you need 4 parameters to describe this matrix. 3 of them are like Euler angles, rotations in this 3-dimensional space, and 1 is an irreducible phase, and it's this phase that allows CP violation to occur. So this also shows up something about the CKM matrix and particle physics in general. So these parameters, 4 parameters you put in by hand, but there's a strong hierarchy to them, that the diagonal elements where you're coupling together quarks within the same generation are large. If you couple between adjacent generations, they're substantially smaller, but they're smaller still if you go between the 1st and the 3rd. So these very small dots here, they're trying to describe the size or the magnitude of these elements are for VUB and VTD, which are rather small. So this structure is very important to why we are doing B physics and trying to study CP violation there, as I'll explain when we look at how we visualize it in the standard model through something called the unitarity triangle. So we use what's known as the Wolfenstein parameterization, where there is this parameter lambda, which is just sine of the Cabibbo angle. So you write this the first two generation mixing in terms of sine of the Bibo angle. And then you introduce these other parameters, A, rho, and eta, to describe these off-diagonal elements. And these parameters are all of order 1. And the expansion parameter lambda is making the off-diagonal element smaller. So lambda is 0.22 in the standard model. So you have then higher order terms, but you essentially look at these this triangle to order of these the CKM matrix to order lambda cubed. And then you exploit the fact that it must be a unitary matrix. And if you look at the first and third columns, you can construct this relationship between the various elements of the CKM matrix, which have to add up to 0. And because you have these complex elements due to the CP violating phase, you can also visualize this in the Argand plane. And each of these terms in this expression can be viewed as sides of the triangle that has to close if you're satisfying this unitarity constraint. And what you should notice about this triangle is that each side depends on a coupling with the B quark, as VUB, VTB, and VCB. Hence, we're very interested in looking at studying CP violation in beauty quarks. And this is the only triangle where you get the sides all to be roughly the same length, because each side is of order lambda cubed. Whereas if you look at other triangles, you have one side that's very small and the other side of order lambda or something. So this is the only triangle in which this happens. So you get non-trivial values of the angles, which Bell calls phi 1, phi 2, phi 3, and the rest of the world calls alpha, beta, and gamma. So these are just the internal angles of this unitarity triangle. And I'll talk more about phi 1 or beta in the later part of this talk. So yeah, this is the other convention that you may be familiar with. So Bell, this was an experiment that ran between 1999 and 2010. It was an asymmetric E plus E minus collider at the upsilon 4s, which is just above threshold for open beauty production. So the upsilon 4s can only decay to a B meson and anti-B meson with no other particles produced. And it was designed to make measurements of this unitarity triangle. And the asymmetric energy, which I'll explain in a moment, was to allow time-dependent measurements of CP violation. So the other advantage one has of producing B mesons through this E plus E minus collision with no other particles is that there's coherent production of the neutral pair, which means they're in a quantum correlated state. So they evolve coherently. So you always have a B0 and a B0 bar until one of them decays. So this is very helpful for the time-dependent measurements. So it's quite a complicated idea. So the Bell detector was very much like any 4-pi spectrometer that you're used to, with the small difference that there's an asymmetry in the beam. So the electron beam had H GeV and the positron beam had 3.5 GeV. So the center of mass frame was moving in the laboratory frame of reference. So again, operating at this upsilon 4s with just the two B mesons produced, there's very few particles in the final state on average. You have less than 10 as particle multiplicity on average at this center of mass energy. And then you identify all those tracks using good tracking, electromagnetic calorimetry, hadron identification, using Cherenkov radiation and time of flight. And you also had a muon filter to detecting muons. You could actually fully reconstruct events where you reconstruct all the particles. And again, I'll talk about that later on. But once you've reconstructed everything and you know your initial conditions, you can also reconstruct the missing momentum. So you can essentially reconstruct neutrinos or weakly interacting particles, exotic particles as well, by looking in this kind of environment, because you have good control over your initial state kinematics, unlike proton-proton collisions. So there was a partner experiment at Stanford called Babar, which did not accumulate as much data, but was highly successful in the early days. but Belle went on to collect 1 inverse attobarn of data, which is a large amount. So, as I'll talk about this later in the talk, I should just discuss the reason why we had this asymmetric collider, and this was because they wanted to measure CP violation in the B sector, and this comes from this J psi K short decay of the neutral B meson. And this is our angle of the unitarity triangle. And with a B0, you have this mixing process going on, which depends on this VTD CKM matrix element, which is one of the 2 complex ones in our Wolfenstein parameterization. So that gives you some sensitivity to the CP violating parameters. But you can't measure a phase from a single diagram. You need to get interference. So you have an interference term to get hold of the phase information. And how you get that interference in J psi K short is that you have a diagram for the B0 and the B0 bar that can decay to this same final state. And these 2 interfere with or without B0 mixing. And you can actually plot whether, as a function of how long the bees lived, the bar has a probability of decaying to this final state or not. And you actually build up an asymmetry that depends on these parameters inside the mixing diagram, the weak parameters. So this violation through the interference of mixing and decay, you can have direct CP violation as well, or you can just have CP violation in mixing as long as you have the interference. But you end up with this time-dependent difference between B0 bar and B0 going to this final state F, J psi K short, and then you normalize it to the sum of the 2 and you build up this time-dependent asymmetry, which depends on the mixing rate, which depends on the mass difference, this delta MD, and then these parameters or coefficients. And in the standard model, you expect this cosine term to be 0, and this SF is just related to sine 2 beta. So this is how we did these time-dependent measurements. But why we had the boost was you need to measure this as a function of time, or technically, because of this correlation, it's between the B0 and the B0 bar in Belle and Belle II. So with this boosted frame of reference, the 2 decay vertices for your B0 and your B0 bar were some distance apart, delta Z, on average around 1/5 of a millimeter, 200 microns. And one side you had your signal decay, and on the other side you had a generic decay from which you could tell the flavor of that B at the time at which it decayed, and that tells you that it's the other sign over here. So you just worked out, given the time difference and the number of Bs that you had at production and at decay, how you could build up this asymmetry over time. And you did it in terms of this difference because of the quantum correlation between the B0 and the B0 bar. And you have to get the flavor of the B right to make this measurement. And you can do that with around a 30% efficiency. So this omega is the mistag rate, and the efficiency is the chances of having some signature by which you can tell what the other B flavor was, usually the charge of a lepton or a charge of a Ka. So these measurements were made, and you see this sinusoidal variation if you look at the difference between B0 and B0 bar for both the Babar experiment and for Belle. And they had agreeing results for this sine 2 beta parameter and confirmed CP violation in the B sector. So these are plotted as a function of time difference, which is related to this spatial distance, delta Z, just related to the boost that you have of the system. So the goal with all of this is to measure the unitarity triangle as precisely as possible using different measurements. And in particular, you can separate this into measurements that are only at tree level, where you have no loops at all. And that can be done through SemiElectronic decays and also by direct. direct CP violation for gamma. Then you have this sine 2 beta measurement and the rate of mixing, which fixes the length of this side, and also some measurements in the kaon system, which are related to loops and box diagrams like this. And new physics at scales very much greater than TeV could influence these different measurements. But what you notice, this yellow-red region here, is how well you measure the apex of the triangle with these different measurements. And at present, the tree level one is not very well known compared with the loop level one. So if these two disagreed with one another, you would know that there's new physics within this loop. So with the unitarity triangle now, we want to try and constrain this as well as possible. So Belle had many achievements aside from this CP violation measurement. There are various rare decays observed, electroweak penguins, which I won't talk about. That'd be a nice talk for someone else to give in this series. Then there were things to do with charm physics, demixing, and also discoveries of many exotic hadrons, these so-called XYZ states that don't fall into the normal pattern of mesons that had previously been seen. And because of the confirmation of the CKM picture of CP violation in the standard model, Kobayashi and Maskawa got the Nobel Prize here in 2008. So it was been very successful. Hence, the whole idea of Belle II is to basically do more. You can never have too much of a good thing. And Belle II is the idea of having 50 times more data than Belle, so collecting 50 inverse attobarns to measure B physics and charm physics and other observables very precisely. But a question you can ask yourself is, isn't this what LHCB is doing already with their B physics measurements? So if you look at the iChep results, many of the highlights are coming from LHCB this year and in previous years. But the big difference between Belle II and LHCB is that the E plus E minus environment allows certain advantages in terms of the reconstruction. So LHCB has the advantage of statistics. So the cross section for BB pair production at the LHC is enormous. It's 5 orders of magnitude larger than it is at Belle. But this can be partially compensated by larger luminosities, this 50 inverse attobarn number. But also because of the threshold production, the background level is relatively low. We also don't have to run a real-time trigger, so our efficiency is very high. We can reconstruct neutral particles in our clean environment, pi0 and k short, very, very well, which is more difficult at the LHC. We have this initial state kinematics. We don't have as good decay time resolution because these bees are boosted such that they fly millimeters often before they decay, so you can measure their vertices very well. We have a very small beam spot, as I'll show you in a little bit. LHCB has the advantage that they generate all types of B mesons, particularly BS mesons and B baryons, whereas Belle II will produce a few BS mesons, but it's mainly B plus and B0. LHCB cannot do tau physics very well, but Belle II is a tau charm factory as well. And there's also this advantage in flavor tagging when you do time-dependent measurements because of the clean environment and this quantum correlation. So that efficiency is an order of magnitude larger. So this allows Belle II to be competitive, even though it's got a statistical disadvantage to LHCB in terms of the production of B and B bar pairs. So where Belle II leads the way in terms of accelerators is its instantaneous luminosity, peak luminosity here, where it's trying to achieve something around 10 to the 36 inverse centimeter squared per second, which is very much higher than the LHC, even the luminosity upgraded LHC and any previous accelerator. So to understand how Belle II can do its physics, we first have to understand the accelerator, SuperKeck B. So this expression, which is rather more complicated than the expression you normally see to describe the luminosity of a collider introduces the parameters of interest. So there's the usual geometric factors, but I want you to focus on these red parameters that I've labeled here. So clearly one way to increase the luminosity is just to pour more electrons and positrons into your machine. So you increase the current. And then you can make the beam spot very, very small. So you're cramming all that current into a smaller space to increase the luminosity. And that's this beta star parameter. It's essentially a measure of how well focused your beams are. But this is in some ways compensated by this beam parameter. If you're trying to squeeze charge into a small space, you end up with problems. And this parameter you have to try and balance in some way as well. So how Belle II tackles this problem is not to just blindly increase the currents as much as possible, because that leads to a lot of synchrotron radiation in an E+ E- machine, which will damage the beam pipe and the detector as well, but to try and squeeze the interaction point down to be as small as possible via this beta star parameter. So this led to what's called the nanobeam scheme. So this is Keck B, the accelerator that worked with Belle on the left side. And these are the typical bunch is crossing one another. So these green and red are the electron and positron bunches. And for Belle II, the SuperKeck B have squeezed their bunches in a clever way, so-called hourglass conditions, so that they are pinched at the centers that cross to give a very small beam spot. And this leads to this very small value of this beta star parameter, which leads to the high luminosity. So this has been done and it reduces the size of the interaction region considerably. So coming back to this beam parameter, it's not just all about focusing the beams better. You also have to worry about this epsilon, which is the emittance of the electrons in the collider, and if you can reduce the admittance, you will increase this beam parameter and increase your luminosity. So you also depends on beta star. So there's an overall beta star square root dependence, and you also have a dependence on the emittance as well. So it's a matter of squeezing the emittance and squeezing the beta star parameter as well. So this led to a major upgrade of SuperKeck B, not only the final focus here at the Belle II experiment, but also in all the components around to deal with the larger currents and also to produce as low emittance beam as possible. So the bending magnets, the dipoles were replaced, the LINIC was replaced, and the RF was replaced too. So there are two separate rings here for the electrons and positrons, given that they have different currents and different energies. And this is this twin accelerator scheme that was used also by Keck B as well. And this is the redesign of the beam pipe in a way that the much higher currents don't melt it. So they use this these type of cavalities and cooling to do that. So this performance has already been proven in terms of reducing the size of the interaction region. So this is a plot showing the longitudinal spread which of the interaction point in our E+ E- collisions at Belle. This is from early Belle data, and it was roughly 0.5 centimeter across. Whereas the same measurement at Belle II, even before much tuning of the beams gone on, has been shrunk down by an order of magnitude. So now this interaction region where the two beams overlap with one another is down to around 0.5 millimeter in length. So this is an early proof that this hourglass scheme was giving what we were expecting in terms of the interaction region. So we've gone on from 2018, and the highlight from the accelerator this year is that a world record was set for the instantaneous luminosity of the SuperKeck B accelerator of 2.4 times 10 to the 34. So it's still some way off the design luminosity, but this is very much falling in line with the plan that we have. And you see also the challenge here. This is in the bottom, the black points. The more current you put in and the harder you squeeze the beams, you end up with spurious backgrounds generated by the synchrotron radiation and other beam effects. So it's a constant challenge to keep the beam background at a low enough level so that the detector can run smoothly. So this high background level has also been managed to be kept at the same rate, even as we're increasing the luminosity, which is key for us to be able to operate the detector. So in terms of the integrated luminosity, there was a small amount of running last year. We got 6 inverse femtobarns, and later in the year there were additional 10. But this summer it's really picked up, and we've now got a sample of 74 inverse femtobarns, of which around half has been used for measurements at presented at ICHEP. But of course, this is very little compared with our 50 inverse attobarn target, but this allows us to prove both that the detector is working and that we're moving in the right direction. And also it should be noted that physics collection is only roughly half the priority at the moment. Much more time is spent during the day. During the night we get physics data. During the day people are constantly working on trying to improve the parameters of the accelerator to increase this instantaneous luminosity number. So that's still the main target at the moment, is to improve the accelerator performance. So talking about the Belle II collaboration briefly now, just the sociology of it all. It's a large experiment, over 1,000 physicists now from 26 different countries, scattered throughout Europe, Asia, and the Americas, as well as Australia. And there's around 5% of the collaboration is from India. There are 4 IITs involved. There's MNIT Jaipur, IISA Mohali, TIFR, Punjab Agricultural University, and IMSC. So we're a large contributor to Belle II, and we've been members of Belle before Belle II as well. Moving on to the the detector. This is reused parts of Belle, particularly the solenoid and the flux return, as well as the wire chamber is very similar design, though it's been slightly changed in size, so it was restrung. Sorry, the electromagnetic calorimeter, the crystals have not been replaced either, so very expensive. But we have a new silicon detector, and we have better particle identification using something called this time of propagation counter, or top counter, which I'll talk about some more, and also I'll talk a little bit more about the silicon. So this is the Belle II detector, very similar to any general purpose detector, with the inner tracking electromagnetic calorimetry and then a muon filter along with some hadron ID. So this time of propagation, or top counter, uses Cherenkov radiation to differentiate between principally pions and kaons. It uses a quartz bar, which is this gray slab you see here, and the track that comes through it will radiate Cherenkov radiation if it's of high enough momentum, such that its speed is greater than the speed of light in that medium. But the angle at which it comes out will depend on its speed, not its momentum. So the same momentum kaon and pion will produce different angled Cherenkov radiation. So you then use total internal reflection within the quartz bar to bounce the photon forward and back until it reaches an array of photomultiplier tubes, micro channel photomultiplier tubes at one end. And using timing, as well as the spatial precision at which you see the photons, you can work out where the photon came from. And you have 16 such bars encircling the interaction region. And you can then use this to identify pions and kaons. So this is what you see if you measure the time at which the photons arrive and the position in the array of microchannel photomultiplier tubes. And if it's a kaon, there's this distinctive blue pattern, and if you have a pion, you get the red pattern. for two coming through at the same place and the same momentum. So as long as you have 100 picosecond resolution, you can be able to separate these different particle types as they go through and be able to identify pions and kaons. So this is not just this is now a working device. So this is some early data where you look at this pattern just for a single event. This was taken over many, many Monte Carlo events. This is a single event, and you can see the pattern of hits of the photons in terms of the channel and the timing. And you have the hypothesis of whether it's a pion in the left, kaon, or a proton. And you see that for the pion, for the kaon, it matches up very nicely with where you would expect the photons to be, which is not the case for the pion and the proton, and hence you're able to identify pions and kaons. The second instrumentation highlight, before I move to the physics highlights, is the silicon vertex detector, which has two innermost layers of pixels, which at present it doesn't have. So it's actually, this is the one bit of the detector that's still missing, and that will be installed somewhat later. And then there are 4 layers of double-sided silicon strip detectors, of which one, layer 4, was constructed by Indian groups led by TIFR. And this detector has much better impact parameter or decay vertex resolution than the Belle silicon vertex detector, and that compensates for a slightly smaller boost that we have now between the two beams, which is required. So this is the resolution of the impact parameter related to the vertex reconstruction. Red is Belle, blue is Belle II, and you see there's a significant difference as a function of the momentum of the particles. Further, you can do standalone tracking of very low momentum particles, which is much more efficient than Belle. This is showing for low momentum pions coming from charm decays. So I will conclude the talk with a few highlights from ICHEP and then one physics prospect. So I've talked about time-dependent measurements of sine 2 beta or sine 2 phi 1. And the highlight from Belle II was that we've had our first measurement of that this year. So this was shown last week by my student from IIT Madras, though she was working on something else. She showed the result. So this again shows this delta T difference, and the blue are B0s and the red is B0 bar. And if you plot the number of decays that you see as a function of this time difference, you see there's a clear asymmetry. And if you fit this asymmetry, you get a value of sine 2 beta, which is compatible within the statistical uncertainty with the world average, but it's a lot less precise. It's an order of magnitude less precise, but of course this will improve as our statistics increase. Also, it highlights a very clean environment in which we work. Here is essentially the B mass peak that we have. This is centered at the mass of the B. And you see there's a very low level of background underneath the signal for the J psi K short that's reconstructed. We aren't quite yet at our optimal tagging efficiency, just in terms of how this measurement was done. And that will again improve as we make further measurements and use more information to do the tagging. So that's one of the highlights from ICHEP. So this is very much Belle II working as we would hope. Another highlight is related to charm physics. And again, there's strong Indian involvement from these institutes in charm measurements at Belle II. Many of these plots that were shown at ICHEP came from these groups. This is for a decay of D0 to K short pi plus pi minus, which currently from LHCB measurements provides the best measurements of mixing of D0 mesons, and these parameters are sensitive to physics beyond the standard model because again, it's a mixing, so it's a loop that's involved. So this is a 3-body decay. So you have a Dalitz plot where you look at the invariant mass of the K short with one pion, the pi plus on the horizontal axis, sorry, it's pi minus on the horizontal axis and the pi plus on the vertical axis. And if there were no resonances involved, you would have a uniform distribution. But when you have resonances, like here you see a K star, you get a band, and the structure of the band actually tells you the spin of the particle. You see on the diagonal a rho meson as well. So this is real data with only 10 inverse femtobarns, so we're getting many, many decays. But what is interesting is to measure mixing, you must do things in a time-dependent way. And here it shows the lifetime distribution coming from these d to k short pi decays. And this is measuring a femtosecond, 400 femtosecond lifetime of the D0. And you see that the signal has this extended lifetime, like linear distribution on this log scale for the exponential decay rate that you'd expect for a long-lived particle. So this is again showing the good performance of the detector, and also we can see the Vertex detectors performing much better than Belle. So this is the different D data, but you have the Belle data compared with what you had at Belle and also at Babar, and you get a much smaller tail on the negative side, which is just to do with the resolution with which you measure the lifetime. So that factor of 2 difference is really being observed in the data. Now, moving to the other main highlight of Belle II at this year's ICHEP conference was measuring semi-leptonic decays. And I'll explain more about why that's very interesting in my highlight, in my prospects. But here we measure the magnitude of CKM elements by either looking at the VUB decay that's related to VUB, with a B going to a pion and 2 leptons, or a B going to a charm and 2 leptons to measure VCB. And you can measure the VUB part by looking at the very highest momentum electrons that are produced, because there's more phase space available when you're going to a lighter pion, so you get higher momentum electrons, which allows you to measure VUB. This is the first measurement of that from Belle II. And you're also being able to look not just at the electroweak part, the VCB measurement, you can also study the QCD of the B to D transitions, and this is showing that in the middle plot. And there's been some work to even measure the differential rates and what you would expect from different models. And this is extremely important for disentangling the electroweak part and the QC, which is could contain new physics, the short range part, and the QCD. So this has been done for the first time and has been shown this week. So Belle II is working well, but our luminosity is still very small compared with Belle. And our next goals are shown on this slide, which shows the plan for Belle SuperKeck B running in the years ahead. So this has changed a bit recently. So we've actually downgraded where we expect our peak luminosity to be around 6.5 times 10 to the 35. And this is the blue line, sorry, the red line is showing this slowly increase over time. And then we're going to upgrade our interaction region, and then we'll get to the very highest values in around the second half of this decade. And over time, we'll just slowly accumulate for the next 10 years a data set corresponding to 50 inverse attobarns as we slowly squeeze down this beta star parameter and get the very highest instantaneous luminosities. So one point to look out for along the way is here in the blue line, which is the integrated luminosity. When we get around 5 inverse attobarns, we will start to make some very competitive measurements in around 2024 with where we may be able to see new physics contributions. So it's a long game, as it is with any accelerator or any detector project, but we're now on the road to getting some very interesting results in the next few years with Belle II. So as in my example, which is related to semi-leptonic decays, I'm going to talk about a very hot topic in particle physics, which is the so-called B anomalies related to lepton universality violation. So naively, once you've taken into account the difference in mass of the tau and the mu, you would expect the rate of B to D tau nu and B to mu nu to be exactly the same because of the universality of the weak coupling to leptons. However, it's possible with new physics, such as a charged Higgs or a leptoquark, to change this pattern, and that would predominantly, or more likely, change things for the third generation, the tau, than the mu. So this is an interesting place to look for new physics and see if there's any violation of this lepton universality. So what you measure is the ratio of the B to D tau nu with the B to D L nu, where L is E or mu. And this can be very precisely predicted in the standard model, assuming lepton universality. And you can do this for both D tau nu and D star tau nu. And this has been a hot topic for a long time now. The first result was in 2012. But why this is interesting is because there's some deviation seen from the standard model prediction, but it showcases the advantages of the Belle II experiment. So here, where we have our upsilon 4s decay, we have a tag side and a signal side, where the signal side, you have your tau, then decaying to a single prong lepton, so tau to mu, neutrino, neutrino, for example, and you have a D. And then on the other side, you fully reconstruct the hadronic B decay. So that allows you to see that there's significant missing energy here, all coming from neutrinos. And you can use both multivariate techniques and then combining that with how much energy you see in the calorimeter, events that are truly all neutrinos to giving the missing energy will have very little calorimetric activity, and you see a peak of the signal down here towards low values of energy in the calorimeter. And this is how we saw these decays at Belle. But of course, we're limited by the statistics that are available. So I'll skip over, but LHCB can also do this, but they have huge backgrounds in doing this, much higher backgrounds than the Belle measurement they have. This is a signal in red here over a huge background. So it's very difficult for them to do, but they have tremendous vertexing, so they are able to do this. But moving to the results now with Belle and Babar and LHCB, if you look down here, this is the, this is the average, this is the standard model prediction for this ratio RD and RD star on the vertical and RD on the horizontal axis. And red is the current world average. And there is a just over 3 standard deviation difference between these. So the standard model is incompatible with the measurements at 3 standard deviations. And only more precise measurements of this RD and RD star parameter will be able to resolve this and see if there is some exotic physics explanation for this. This is one of the few places where the standard model is not working fully as we expect. So Belle II will do very well at these kind of measurements. And they use this full event interpretation where they reconstruct over 5,000 different B decays to get a very pure sample of hadronic B decays on one side, for which you can look for these rare decays with lots of missing energy on the other side of the event. So these are plots from iChep showing that we've already got 40,000 of these tags for B+ and 35,000 for B0. And one expects that this is with 50 inverse attobarns, you get this very small region allowed from the measurements, we measure very precisely. But even with 5 inverse attobarns, we'll be able to tell whether there is a significant difference between the standard model and what we're observing. And this would be a clear signature of new physics if we see this. So there are many other measurements. This is my penultimate slide now. We can determine the other angles of the unitarity triangle, particularly gamma, very precisely to around 1.5 degrees. This is competition with LHCB. They are also making precise measurements. You can measure the length of the side that's proportional to VUB, and that will be done to around 1.2%. That relies on improvements in QCD as well. This is what we expect it to look like. Sorry, this date I should change. This is now nearer to 2030. There are other rare decays one can measure. These are all given here. In particular, there's other lepton universality anomalies seen in these loop-only diagrams, these beta XS LL. and we'll be able to measure those to a few percent to see if these deviations really are. They're currently observed at the 20% level, whether they really are the result of new physics or not. We can also do more with neutrinos here. We can measure CP violation again in loop-only processes, the so-called gluonic penguin. We can do very rare tau decays. I don't have any time to talk about this, but this is a very interesting area. You have this number violating decay, tau to mu gamma. You'll set the most precise limits on that. And this is an example of tau decays in our early data, showing excellent data Monte Carlo agreement. This is the pseudo mass of the tau decays. So we're already producing many taus and studying those. And there's also this QCD, charm physics, QCD physics, and dark sector, which I haven't talked about. Certain regions, we can look for dark matter, we can look for axion-like particles, we can look for dark Higgs and dark photon. And there have been already two publications, sorry, not publication, one publication and one submitted for publication on these, but that's a talk for another day, to the dark sector. So I'll conclude now. I've taken an hour of your time. So intensity frontier is a very active area, and Belle II, Belle II and SuperKeck B, the first high energy physics collider experiments since the LHC, are really leading the way in terms of the intensity frontier. And flavor physics has played an important role in developing the standard model, the fourth quark, third generation, heavy top. And there's no reason to think that they might point the way for us to look at physics beyond the standard model by making these precision measurements in the flavor sector. So along with LHCB, we hope to be continuing the tradition of learning more about the standard model and particle physics in general from these precision measurements. So thank you. I'm done.
Yeah, thank you very much, Jim, for your really excellent talk with nice pedagogy that you kind of started off, and then of course both at some point and also as the talk went on, you made excellent comparison of capabilities and results, or the USPs I can say of the LHCB and Belle II, and very nicely you have actually brought out the developments or the upgrades in the accelerators, and briefly on the various detector upgrades for the Belle II compared to the Belle experiment. And what is, of course, very much heartening to many of us on the call is very significant, the Indian contributions that were made both on the detector developments as well as the physics that you have shown, including those results, which are really when fresh from ICHEP. Yeah, particularly the SVD, I think is feathering, I think the Indian collaborations cap, I must say, and so congratulations to you and your colleagues. And also, I mean, you brought out quite a few future prospects and the physics that is waiting to be done at Belle II. And as hopefully your luminosity, you're able to kind of increase with time with additional components, both on the accelerator and the detector. So, in all, I mean, it was very nicely pitched for the participants, I guess, and I'm expecting that there will be reasonable questions and discussion. So let me not take too much time, except to thank you on that. But we'll get back. Now we already have some questions, so let me start from here. Sailesh Pincha has a question for you.
Hello.
Yeah, we can hear you.
Yeah. So my question is, just like there is a possibility that due to the sterile neutrinos, the current 3x3 matrix in neutrino sector is non-unitary. So is there the similar possibility in the quark sector that the current CKM matrix may be non-unitary with the possible fourth generation quarks?
So that has been put forward as an idea over the years, that there might be a fourth generation. However, current measurements are such that the fourth generation is not particularly favored in terms of a model of new physics, say, to describe what's going on. These particles wouldn't be sterile in the same way that you're thinking of.
Yeah, that is true. Like they will most probably be charged, so they will definitely interact electromagnetically.
Yeah, but how they can hide is by being very heavy.
Yeah.
Right. So it's possible there are additional particles that follow some generational scheme, but at very high masses, which even we wouldn't be sensitive to. But in principle, you're right that it's there. It's a possible extension, but it seems unlikely. For example, like there aren't any fourth generation models that describe the B anomalies, for example. That's very much lepto quarks or similar things to do that. So or additional gauge symmetries, so Z primes and those kind of extensions of the standard model rather than the fourth generation. But in principle, there's nothing to stop it, but you would have to put it at very high mass to stop it perturbing measurements that we've already made.
Thank you.
Okay. There's one question in the YouTube by Abhinav Chaudhary. Why do quarks have flavors with each flavor having different characteristics, and why they switch into one to another?
So
yeah,
the why is a good reason, a good question. I don't think anyone knows exactly why flavor allows this, that you can move between the generations. Okay, that's just it's feasible through the CKM picture, but it could be like the lepton sector where that's not possible, right? That naively you would say it would look like the leptons where you can't change between generations. Yeah. So this idea of flavor, right, is just a way of labeling the different types of quark. So isospin is the original flavor, where you plus a half is giving you an up quark, upness, minus a half, downness. Okay, so it's saying that these are quarks, but they are of distinct types. So it's just a way of saying that there is more than one variety. Okay, so we have 6 varieties, or 18 if you choose the different colors, and it's just a way of counting in the same way that we think of lepton number or lepton flavor for the electron, muon, and tau. So I'm not sure about the first part of your question, but the second part,
yeah,
that ability to change is what makes the weak interaction so interesting, that it's the only place in the standard model where we can change between generations. Otherwise, heavy particles would have been stable without new physics. So you would have had strange stable particles or even beauty stable particles of some kind, if there hadn't been this ability to then move between generations and decay to a kinematically more favorable state.
Okay. Another one, what are the particles detected by electron-positron annihilation at Belle II experiments till date?
Well, okay. So well, there are 2 aspects of this, right? There's one is that generally we just reconstruct a handful of particles, the ones that we can, the stable ones, whether they be photons or K-long in terms of neutral particles, or the electron, muon, pion, kaon, proton. Then from that, we have reconstructed pretty much, well, you know, you look in the PDG and there are all sorts of possibilities for your mesons that are made up of charm, strange, and up-down quarks. So it depends what we've seen many things. DS mesons, D0 mesons, lambda C came at the ICHEP conference. We've also been looking for more exotic things like the X3872, this charmonium-like state. So we're seeing all the things we expect to see that have masses in the few GeV range. So we're looking at all those zoo of particles that are there. We haven't seen anything exotic. We haven't seen an ALPS-like particle, and we haven't seen dark matter candidates. But those things that are there in the standard model, we have seen. We haven't yet seen any signatures for exotic hadrons, but we've certainly seen J-psi, Psi2S, all the things that we expect to see.
Okay, so Jim, we have a few questions or comments. So let us go to Balasubramaniam.
Hello, good evening. Am I audible?
Yeah. Yes, please go ahead.
Sir, could you please tell us something about lattice QCD measurements on CK matrix elements?
Well, I'm not an expert on that. However, maybe I'll just show a picture I showed near the end, which is helpful. Yeah, here. So you see, we've written the CKM matrix in terms of the different diagrams that are sensitive to the magnitudes of the CKM elements. Now, where you see sort of fuzzy bits, whether they be yellow or blue or red, they're either showing you light quarks, charm quarks in blue, or red B quarks. There is a lot of QCD going on, binding together the B meson or the charm meson. And to interpret well these semi-leptonic measurements, you either have to do calculations in like cone sum rules or in some way in QCD, or you use lattice calculations to determine the form factors that you have. So these form factors are often calculated by the lattice, and then we compare them to the measurements and take out those the contribution from the QCD to get at the electroweak, the short range effect. Now, these measurements are also done with charm decays, principally at the Belle II experiment. And the charm measurements here are very useful to calibrate the techniques of lattice QCD so that you can then apply them to the B system to get more precise measurements of VUB, for example. So this particular decay B to pi L nu to get the lattice predictions for the B to pi form factors are essential to determine VUB, which is one of the big goals of Belle II, but it also requires improvements in lattice QCD. So whatever petaflop calculations or whatever people say need to be done as well to do these calculations as good as possible, and to do as realistic as possible calculations with less and less quenched calculations with more and more massive quarks and things like this. So you really should talk to a lattice QCD specialist about this. It's a very you shouldn't ask me too many details of the calculations, but they're exceedingly important for these types of measurements. Okay.
Yes, sir. Thank you, sir.
Okay. Let me take the question or maybe comment from Gagan.
Can you hear me?
Yeah, okay, you can take over, Gagan.
No.
I'm tired now.
No, I absolutely not. So anyway, I really enjoyed the talk. because there was this, I don't know, from YouTube, this comment, so you really said the half of the PDG, more than half is basically the measurement from the flavor sector. So indeed, we haven't seen anything new as similar like LSC, but there are some exotic measurements which have been seen by Belle and Babar, like this X3872, or the discharged tetraquark candidate. I mean, they are not new physics. I don't know if the questionnaire is still there.
Yeah,
but the QCD people are still having trouble to really fit in that with this what we call the standard quark model. Okay.
Yeah.
So
but we
they
haven't
are not new
reconstructed them yet
physics.
at Belle II, right? I don't
Right.
think.
Oh, was that in Belle? Okay. Sorry,
that was in Belle II was the question. Sure, in Belle.
Okay.
Yeah, he was asking for Belle II.
Oh, okay. Sorry.
Yeah,
sorry.
yeah. No.
But nevertheless, it's thanks Gagan for actually pitching in and also adding up to what Jim has already said. I hope the participant got his answer now. Thanks for that. And we'll also take up another question from Ishwant Prabhu.
Good evening, sir.
Hello.
Yeah.
How are you?
I'm great. How are you, sir?
Fine.
Yeah. So I just had a question. So Belle and Babar, these are mainly related to studying B. So how would BESS3 contribute in flavor physics in terms of the unitarity triangle? I hope you got my question.
Yeah, it's clear.
So I can answer that. So BESS3 contributes in two ways, really, to CKM physics. One is by measuring VCD and VCS very precisely in semi-leptonic decays and in fully leptonic decays. And the other way is less direct, but it measures what are called strong phases of D0 and D0 bar, which are essential inputs to determining gamma in B decays. So that these are the two principal contributions of BESS3 to CKM physics. And particularly in terms of the absolute size of VCD and VCS, that's the best place with which you can measure these. And because it's at charm threshold, it has the same advantages as Belle II, that you only have a 2D mesons, you have nothing else. So you can fully reconstruct the whole event, and you can make absolute branching fraction measurements very precisely. And you can measure almost background free measurements of partial decay rates, and you can then test the QCD predictions for the form factors very, very well. Then there's also a lot of other physics that's done in terms of measuring branching fractions, which again are important for flavor physics. So as an example, they also produce lambda C bar pairs, and you measure the lambda C branching fractions. And those are used to normalize VUB measurements at LHCB, for example, in lambda B, semi-leptonic decays, lambda B to proton. So there are all sorts of engineering measurements that are there as well. And then there's this direct contribution in terms of VCS and VTD.
Okay.
VCD,
so in terms of neutrinos, I think they'll be very similar, isn't it? The Belle II and BESS3 will have the similar kind of studies based on neutrinos.
Yeah, we can fully we fully reconstruct neutrinos by inferring their presence through form momentum conservation. We can do both. We can do that at both Belle II and BESS3.
Okay, sir. Thank you so much.
Okay, I think Jim, I don't see any more questions from either of the platforms, so that also brings me to once again thank you on behalf of all the participants for taking your time and giving this excellent talk, both in terms of the physics as well as the detector an accelerator, of course, of the Belle II, and also especially the future prospects and open problems for the younger people to work on. So we really thank you for your excellent lecture today. And before I say goodbye to all of you, I would like to once again remind you for the next talk on Friday, on August 7th at 6 p.m. same time. We are going to have another very interesting talk by Dr. Archana Sharma from CERN, Geneva. She is going to talk on tools and techniques from high energy physics to societal impact. So we once again invite all of you to come back for this another interesting lecture. So Jim, once again, thank you very much for the time that you took. And so I once again appeal to all of you, please take good care of you and your family and stay safe. Thank you very much.
Thank you. Bye-bye.
Bye-bye. Thank you. Good night, everyone.